back to my channel, and today I'm going to be talking about the history of physics. In this video specifically, I'm going to be talking about string theory. So what is string theory and why is it important? String theory is a theory that attempts to find the unification of the four fundamental forces. Now, the unification of the four fundamental forces leads to the theory of everything. Now, physicists still have some trouble in formulating a theory of everything. Now, string theory is a possible attempt to resolve this issue. Now, to truly understand string theory, we must understand the unification of the four fundamental forces, the theory of everything, and much more. So what is the theory of everything? Theory of everything is a mathematical theory that must describe all phenomena in our universe accurately. If it can do this, we call it the theory of everything. Why do we need a theory of everything? Well, if we just have, let's say, 100 theories for 100 different subjects, then that'll make nature more complicated, and that'll make math more complicated, and that'll make physics more complicated. Now, one, we want to make physics much simpler by creating one major theory. Two, we want to prove that nature is simple. Like, what we mean is nature is complex in all its phenomena, but we can write it in, for example, a chapter, or maximum a book, full of equations that describe our universe accurately. That's what we want to do. It's also the unification of the four fundamental forces. Okay, so what are the four fundamental forces? Well, we have to talk about the standard model of particle physics to truly understand that. So we have the standard model of particle physics. Okay, so we have in the standard model of particle physics quarks, leptons, and we have bosons. Our main focus in this video are the bosons. Now, the quarks are things that make up protons and neutrons. We have leptons, which are electrons, neutrinos, muons, taus, and so on and so forth. And then essentially, we have the unification of the four fundamental forces. Okay, so what are the four fundamental forces? Well, the four fundamental forces are the gravitational force, the electromagnetic force, and the nuclear forces. Notice I said forces, which means there's two of them. Okay, I'll write them over here. We have the electromagnetic force. We have the strong force. This is the nuclear force. And the weak force, which is also nuclear force. Then above here we'll write the gravitational force. Okay, so we have the gravitational force, the electromagnetic force, the strong force, and the weak force. Now, what do these describe? Well, as you can see, we have four forces in nature. There's also another one called the Higgs boson, which also represents a force, but we're not going to be talking about that right now. Of course, it is included in the theory of everything, but right now we're talking about these four fundamental forces. Gravitational force, electromagnetic force, strong force, and weak force. Well, without the gravitational force, we wouldn't have a moon to create tides. Without the electromagnetic force, we wouldn't have electricity, light, and so on and so forth. Without the strong force, we wouldn't even exist. And without the weak force, radiation wouldn't happen. So as you can see, these four fundamental forces are very important. Now, each of these have a particle attached to them. Well, at least they're said so. So as you can see, we have a strong force is connected to the gluon. The weak force is connected to the W and Z bosons. We have the electromagnetic force, which is connected to the photon, which is popularized by the photoelectric effect. Or you could just say the photon is a particle for light in the visible spectrum, and it's just pretty much all the light spectrum we have. But in the visible spectrum, we say that light is made out of photons, and all spectrums too. But photons are just really cool. And we have the gravitational force. The gravitational force essentially represents, we have gravity. But what is the particle for this? It's a graviton, right? Well, wrong. A gravitational force does not have a particle attached to it. Now, these are all true. We have the photon, the gluon, W, and Z bosons. However, we don't have a particle for gravity. Now, according to many people, this isn't a problem. And as it seems so, it isn't, because we have the general theory of relativity and quantum mechanics to describe most things in our universe. Why need a theory called string theory? So, we have to talk about the differences between quantum mechanics and a general theory of relativity. Why do we need to talk about this? Well, the reason is because to understand the standard model of particle physics, the theory of everything, and why we even created a string theory in the first place, we have to talk about where the problem arises. Because one, we created theory because we want to describe our universe. That's because we just randomly observe a fact and start a universe. But all theories and most theories are based off of a question. So we have a question over here. There's a discrepancy in quantum mechanics and the general theory of relativity. Well, what is that? Well, quantum mechanics describes a small. We'll just write small. And we have, essentially, general relativity describing the big. You can see we have the small and the big. Now, as you can see, can the big describe the small? Or what I mean, can the general theory of relativity describe particles? And can the quantum mechanics or quantum mechanical theory describe what the general theory of relativity describes? So we have an interchange of these theories. Can they do it? Well, the answer is no. The equations and math of general relativity do not match up with the phenomena that quantum mechanics predicted, and is matched with experimental evidence. Now, why is this a problem? Well, as I mentioned, if we just have, for example, say 100 theories, then we have each of these theories, and let's just say we want to try to describe a universe in an accurate way, then what do we do? Calculate all the theories, or say, for example, we have one phenomena. There isn't an exact law that describes this phenomena, but we have 100 theories to describe everything. And what do? We take 50 of them and describe that phenomenon. But this is going to involve mathematics, hard work, which hard work is required in all things, but you have to work really, really, really hard. We probably need supercomputers to compute it, and plus, it's just useless. Instead, we want to say that nature is complicated in phenomena, but simple on the inside. Or what we mean is we want to create a theory of everything, the theory that describes everything in our universe in physics. So that's essentially what a theory of everything is. As you can see, two of the main theories, quantum mechanics and the general theory of relativity, aren't compatible with each other. Or in other words, they're incompatible. Now, what can we do to make them compatible? Well, there are two things that we can do. One, create a new theory. Two, create a theory that involves both quantum mechanics and the general theory of relativity. Well, the latter is loop quantum gravity, which we'll talk about in the next video. The former is string theory. So string theory is trying to resolve this problem, trying to make the phenomena described by quantum mechanics and general relativity all into one theory, hence the name theory of everything. Now, we also have another approach called quantum gravity. It's not loop quantum gravity, but quantum gravity. Quantum gravity. Now, quantum gravity predicts a hypothetical particle for gravity called a graviton. Now, actually, we can't prove this. Well, we can, but we haven't proved this experimentally. I mean, you don't even know if we can. So one, we have to find it experimentally and then formulate the mathematics for this. Or two, we have to do the mathematics and then hope for that we'll discover a graviton or make tons of attempts to find one. Well, as you can see, we haven't discovered one so far, or it will become a very great breakthrough. So since we haven't discovered one, then what can we do? Well, we have to go on the mathematics side. So we have to resort to the mathematics. Now, what happens when we plug in the configurations and the equations of quantum mechanics and particle physics for the graviton? What do we get? Well, we get tons of infinities. Now, in mathematics, infinities are useful. For example, when we have a summation sign, we want to see if something converges or diverges. Most of the time, convergence is very useful. Divergence is actually not useful. But essentially, the theory of something diverging, which means that it goes out to infinity, is actually a pretty good idea. So essentially, we have something that is going to converge or diverge. Now, the divergence part is important in mathematics. However, when we take physics, for example, convergence isn't actually, divergence isn't actually much of a use because we can't have an infinite amount of things. For example, we can say we have an infinite amount of mass over here. If we do have an infinite amount of mass, then essentially we could create a black hole or something like that. So essentially, we can't really say that we have an infinite amount of things in physics. That doesn't make any sense. So when we plug in the configurations of the graviton into the equations of quantum mechanics, we get tons of discrepancies and we get infinities. Now this happened previously when we had another theory, and we can use a mathematical technique to resolve this. But we can't create, well, we can't so far create a mathematical trick that essentially just resolve this problem. If we can, then this would be a breakthrough and we could mathematically prove the existence of a graviton. But we can't so far. So the graviton's idea is ruled out. So string theory is what is left. Okay. Now let's talk about a deeper version of the theory of everything. A theory of everything is supposed to describe not only the unification of the four fundamental forces, which is one of the main things, it is supposed to describe any phenomena in our universe. It's supposed to describe classical mechanics, electromagnetism, everything. Not only it's a theory of everything. If we have a theory of everything, this will be a major breakthrough. But just because we have a theory of everything, physics isn't stopped. We can still make tons of other discoveries. Now, this is what makes a theory of everything so far. We have to describe all of our nature's laws that we have discovered and might be even discovering into a theory and use mathematics to compute it, and essentially that's what we want to do. Create a theory of everything. Now, this is very hard to formulate mathematically, which is why string theory came up. It's a new theory that tries to propose something. Okay, here's what string theory proposes. Take the smallest particle we have, or that we know of in existence. We'll call this particle S. S stands for small, so particle small or particle S. Now, zoom inside this particle. Well, right now we can't zoom in into the smallest particle. Why? We don't have the technological advancements and the technology today. So this is nearly impossible today. So if we zoom in to very, so we zoom in a lot, then what we're going to get, this is what string theory proposes. We'll write the proposal of string theory is that there is going to be a string. So say this is a photon, or let's just make it a gluon. Now this is a gluon. Now this string vibrates in a specific type of placement. Now if it vibrates like this, for example, let's just say, for example, this produces a gluon. But if we alter the vibration, this can produce maybe a graviton, the particle for gravity. So string theory says that everything is based off of strings. Now since these strings vibrate at different frequencies, then we can essentially describe different phenomena. Now, essentially, we can describe all the laws of physics, describing by all the forces and all the things. So string theory just creates different types of things. So we have the graviton, so it creates the force of gravity, different vibrations, it creates a strong force. So it essentially creates pretty much everything we know. That's what string theory is. But string theory, in some older versions of string theory, we have 26 dimensions. Now to get a feel for what 26 dimensions is, we have to start from the 0th dimension. Now the 0th dimension is a point. You can't move anywhere, it's a point. So we'll call this a point. 0 dimensions. Next, we have a line. It can extend infinitely in these directions. So we'll call this a line, and it has 1 dimension. Like this. And then we have a plane. Now a plane can go like this. It can go on this 2D surface. So plane is what we call 2D or 2-dimensional. Now we come to our world. Our world is a 3-dimensional space. Notice that in mathematics we have something called Archive, which is the real number system, but in 3 dimensions. That's essentially what it's describing. Now if we take the 3rd dimensions, we have up and down, right? Like this. So this will describe 3 dimensions. We can go up and down, and left and right, but we can also go in and out. So we can go up and down in 1 dimension. We can go up and down and left and right in 2 dimensions, we can go up and down, left and right, and in and out in 3 dimensions. So in and out. That's essentially what a 3-dimensional system means. Now, we know of 2 dimensions, 1 dimension, and 0 dimensions, obviously because we're in the 3rd dimension. We can look at what's below us. So we can say, oh, okay, we're in the 3rd dimension, then 2 dimensionals are probably small, probably can't move like this. But we can't describe a 4th dimension because we're not in there. We don't know how it is. How can we describe it mathematically? Well, we could have equations that describe it mathematically, but we can't create a visual representation. Now imagine we continue like this. 3 dimensions, 4 dimensions, all the way to 26 dimensions. Then this would be really complicated. Now, older versions of string theory require 26 dimensions. Now the question is, where are these hidden dimensions? We can only see 3 dimensions, but where are the others? So that's one problem. Modern theories of string theory, like superstring theory, which involves supersymmetry, involves only 10 dimensions. Now this might seem, wow, this is a huge improvement from 26 dimensions, but if we think it from the fact of 3 dimensions, we still have 7 dimensions extra. Now, many people think, oh, we just have string theory. This is one almost complete theory. But essentially, we can't have string theory. One, as I mentioned, the technological advancements aren't enough. And 2, we need a lot of power. So other than that, and the 10 dimensions fact, because we don't know where are the 10 dimensions, we actually have 5 different types of string theory. So we have one type of string theory, another 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 type of string theory. Now, which is right? Well, actually, you might be thinking all of them are right, or none of them are right, or one of them is right, or the one that I'm describing is right. Well, the actual thing is that they're all right. They're just 5 different versions of one theory. This is called M theory. M theory is a theory that essentially is the bigger theory of the 5 different versions of string theory. So there are 5 different versions of string theory, and 3 is the big theory. This requires 11 dimensions. Not much compared to 10 dimensions. But it arises from a concept called supergravity, which we'll not discuss now. This is essentially how M theory arises. People wanted to describe supergravity, so they created the theory, namely M theory. Then they created something called branes, or membranes now. And essentially, as it developed, we can see that it now also describes the 5 different versions of string theory. So essentially, that's M theory. M theory is just a bigger version of the 5 different versions of string theory. Now, one thing to notice is that all of physics, and especially modern physics today, and the research at the brink of research, involves tons of mathematics. The reason? Mathematics is the language of our universe. Now, string theory arises a quote to mind. This quote is from Nikola Tesla. Namely, if you want to find the secrets of the universe, think in energy, frequency, and vibration. Okay, now that we've thought of that, and when we've looked at string theory and how string theory involves 10 dimensions, and we have M theory, which involves other dimensions, let's just summarize what essentially we talked about. So essentially, we started by talking about the unification of the 4 fundamental forces and the theory of everything. A theory of everything is a theory that can describe pretty much all physical phenomena in our universe through mathematics. If we can describe this, we have a theory of everything. And to describe the unification of the 4 fundamental forces, but also describe other things too. Like we can describe the Higgs field, the Higgs boson, and so on and so forth. We should be able to describe everything in our universe. That's the theory of everything. We have the unification of the 4 fundamental forces. The 4 fundamental forces are the gravitational force, the electromagnetic force, the weak force, and the strong force. Notice the weak force and the strong force are considered nuclear forces. After we talked about that, we talked about the standard model of particle physics and how each force maps to a particle called a boson. We can see that starting with the strong force, we have the gluon matched with it. Starting from the weak force, we have a W and Z bosons matched with it. The gravitational force has a hypothetical particle called a graviton, and we have, last but not least, the electromagnetic force, which has a photon. Notice that the essential graviton is a hypothetical particle. When we haven't discovered it experimentally, which means we have to resort to mathematics. When we test it mathematically, what happens is, well, we get infinities. Infinities are useless in physics. Well, not totally useless, but useless. And we haven't used any mathematical techniques, or we have used them, but they don't work so far. So we can erase the idea of a graviton. Then we looked at the differences between quantum mechanics and the general theory of relativity. quantum mechanics and the general theory of relativity have differences. We can't use quantum mechanics to describe the phenomenon that general relativity does, and we can't use the general theory of relativity to describe the phenomenon that quantum mechanics does. This makes both of the theories incompatible with each other. So therefore, we have two options. One, create a totally new theory, or two, create a theory that involves both quantum mechanics and general theory of relativity, except one is altered, or both of them. As you can see, the former one is string theory, the latter one is loop quantum gravity. We'll discuss loop quantum gravity in our next video. After that, we started talking about what string theory is. We talked about, instead of modern particle physics, which we have a particle, string theory proposes the idea that if we take the smallest particle and zoom in and in and in for a very deep distance, or a lot in, then we can find something called a string. And different vibrations of the string produce different effects, like we can have a graviton, which describes gravity, and so on and so forth. That's what string theory describes. Now, string theory uses the idea of strings, and we talked about how older versions of string theory involve 26 dimensions. So we described that we have 1 dimension, 2 dimensions, 0 dimensions, 3 dimensions. This is all we can describe, and 26 dimensions is a lot. Then we described the newer version of string theory that only involves 10 dimensions, which is actually a big leap forward, but still a lot compared to the 3 dimensions. The question is, where are all these extra dimensions? Then we talked about M theory, which is based off of a theory called supergravity, and we're trying to solve this. Then when we're trying to create supergravity, essentially, well, a string theory has strings, M theory has membranes. That's essentially what M theory is. And then we found that M theory is actually a bigger version that combines all the 5 versions of string theory. Now that we've talked about a summary, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.